Quantum entanglement has been called spooky action at a distance by Einstein, and for good reason. Today, we're going to explore whether this bizarre quantum phenomenon could actually revolutionize how we communicate and transform the internet as we know it. But first, let's understand what quantum entanglement actually is. When two particles become entangled, they form a connection that defies our everyday understanding of reality. Measure one particle's property, and you instantly know the corresponding property of its entangled partner, no matter how far apart they are. This isn't just correlation we're talking about. The particles genuinely affect each other instantaneously across any distance. Einstein famously disliked this concept because it seemed to violate the principle that nothing can travel faster than light. He preferred to think there were hidden variables we simply couldn't detect. But decades of experiments have proven Einstein wrong on this point. Quantum entanglement is real, and it's as weird as it sounds. So, how might this strange phenomenon revolutionize communication? The most talked about application is quantum communication networks. Unlike classical communication, where information travels as electromagnetic signals, quantum communication uses the properties of entangled particles themselves to transmit information. Here's where it gets interesting. In classical communication, your data travels through cables, radio waves, or fiber optic lines, where it can potentially be intercepted, copied, or tampered with. But quantum communication offers something unprecedented: perfect security through the laws of physics themselves. When you try to measure or intercept a quantum state, you fundamentally disturb it. This isn't a limitation of our measuring tools. It's a fundamental principle of quantum mechanics. Any attempt to eavesdrop on quantum communication necessarily leaves detectable traces. The sender and receiver will know immediately if someone has tried to intercept their message. This leads us to quantum key distribution, which is already being implemented in some parts of the world. Instead of sending the actual message through quantum channels, we send cryptographic keys. These keys are then used to encrypt and decrypt classical messages sent through normal channels. If anyone tries to steal the key during transmission, the quantum properties ensure will detect the theft. This opens up fascinating possibilities. Distributed quantum computing could allow quantum computers in different locations to work together on the same problem, effectively creating more powerful quantum systems. Quantum sensors in different locations could share entangled states to achieve unprecedented precision in measurements. The quantum internet could also enable quantum cloud computing. Instead of accessing classical cloud services, users could tap into remote quantum computers while maintaining the quantum properties of their data. This could democratize access to quantum computing power, but we're still facing significant technical hurdles. Quantum computers themselves are still in their infancy. Most require extreme cooling to near absolute zero temperatures and are incredibly sensitive to environmental disturbances. Building a network of such devices presents enormous engineering challenges. Then there's the question of quantum error correction. Classical computers can detect and correct errors relatively easily, but quantum error correction is far more complex. Quantum states can't be simply copied, so traditional backup and recovery methods don't work. Developing robust quantum error correction for networked systems is an active area of research. Let's also consider the practical timeline. While quantum communication experiments are happening now, a widespread quantum internet is likely decades away. We're still working on basic quantum networking protocols, developing reliable quantum memory systems, and solving the fundamental engineering challenges. However, hybrid approaches might bridge the gap. We could see networks that combine classical and quantum communication, using quantum channels for key distribution and authentication, while relying on classical channels for bulk data transmission. This could give us many of the security benefits of quantum communication, without requiring a complete infrastructure overhaul. The economic implications are substantial. industries handling sensitive information like finance, healthcare, and government communications could benefit enormously from quantum-secured networks. The global quantum communication market is projected to grow rapidly as the technology matures. But we should also consider potential drawbacks. Quantum communication networks could create new forms of digital divide. Countries and organizations with advanced quantum infrastructure might have significant advantages in securing their communications. This could reshape geopolitical balances and create new dependencies on quantum technology. So will quantum entanglement revolutionize the internet? The answer is nuanced. It won't replace classical internet infrastructure, but it will likely create parallel quantum networks for specialized applications. These networks will offer unprecedented security and enable new forms of distributed quantum computing. The revolution won't happen overnight, but quantum communication is already moving from laboratory experiments to real-world applications. As the technology develops, we'll probably see gradual integration rather than sudden replacement. The Internet of the future will likely be a hybrid system, combining the best of classical and quantum communication technologies. What's certain is that quantum entanglement will play an important role in how we communicate in the coming decades, even if it doesn't completely revolutionize the internet as we know it today.